This is a continuation of Class 5 in ME470, and we were talking about planetary gears. And I want to go through a simple example that's available from in Norton's book, Design of Machinery. I think it's a useful example to go through. So for the planetary gears shown, find the output speed and direction if the arm is the input at 1000 RPM clockwise and the ring is fixed and the sun is the output. Okay, so what they're showing here, you need to look at really carefully, that you would have, let's say, a shaft that is connected to this arm right here, right? So this shaft is the arm shaft. No, excuse me. This is the arm shaft right there, right? You see that dark color right there. Yep. And that this is the sun shaft, and then this is the ring shaft, right? So that any of those three could be connected to something externally. And so we have, in terms of teeth, you could see that we have 40 sun teeth, 20 planet teeth, and we have 80 ring teeth. So just as you did in a previous one, you want to check and see that these are compatible with each other. First off, they all have to have the same pitch. So the number of teeth is going to be proportional to the diameter for these things, or the radius. So you have 40 teeth right here. So let's say that there's 20 in terms of like the radius, plus another 20 right here. So there's 20 and 20, and right here half of this is 40. So you could see that these will work together, right? So that combination has to exist. And then so like let's what we have to do here is take the E value, and now we don't have to go in the order in which, like, what's being said right here. This E value will be valid for whatever combination that you choose. So I just like to think of the sun as the traditional input, and let's say that the wheel, the ring, is the output right here. And let's pretend like the arm is like stationary right here, because we're just looking at teeth when it comes to that the gear train thing. So right here we could say that number 2 drives number 3. Right? So N2 drives N3. And then we could take a look at this. We can see that N3 drives N4. Right? So N3 drives N4. Now you had to be careful here, because here's where a trap is. What we had in the previous gear train, we said each stage is negative. That's not necessarily true if there's an internal gear, right? So we could try to memorize that, or we could do what is generally said is, like, if you want to try to figure out what the input and output, which one is going to be positive or negative, what you want to do is hold the arm steady right here. You hold the arm stationary, and you find which direction this will go, right? So if you were to move the sun, as they show right here, in that direction clockwise right here, okay, what would happen here is that this would be clockwise, and then so this would have to be counterclockwise right here, right? And so over here, that would force that ring to go upwards. Does that make sense? Right? It couldn't go backwards, right? This couldn't go counterclockwise and then this go clockwise. The teeth would break off right here. By this one going counterclockwise makes that one go counterclockwise. So when we're taking a look at whether this thing should be positive or negative, this whole thing, this is going clockwise and this output is going counterclockwise. Therefore, the whole thing is negative. Not the same thing as what we had previously, where each one of these stages reverse direction. And that's because of the nature of this internal tooth gear thing taking place. Similar to our little trainer, thing right here. Like, once again, we could say make the planet fixed right here. So the planet would be fixed somehow, right there. Planet's fixed. Input gear, input sun, right here, makes the output go counterclockwise. So in this configuration right here, we've figured out. Now, we can have more complicated things than what we've seen right here. So we have to be on the lookout for more complicated configurations, as I alluded to. Right, we can have more complicated things, and not necessarily would it always be this way. So we have to think our way through and see which direction this thing is, the overall gear train thing. So as part of that, so I'll make that negative, and the gear teeth driving right here is 40. This is 20. But we also notice that this is going to be driven. This gets driven down here, so that those are actually canceling each other out. So this is 80. So the overall gear train ratio is negative 0.5. Now we're going to use that with the equation NL minus NA divided by NF minus NA. So, and the first scenario that we're describing up here, let's see, it says that the arm is the input, right? So, and the arm is the input, and it goes at 1,000 RPM clockwise. So NA is 1,000 RPM. And I'm almost tempted to make it negative, but I'm just going to recognize that I'm going to get the opposite thing from what I want. So I'm going to treat like clockwise. For this time, for this only, clockwise is considered positive, right? And the ring is fixed, right? So the ring in this one is the last. So we'll say that the NL is equal to 0. And so we want to find the sun is the output. So that's going to be the first. That's the thing that we're going to try to find. So just plugging into this equation right up here, we say that if the last is 0, the arm is going to be 1,000. The first is the thing we want to find, and the arm is 1,000. And that equals negative 0.5. I do the math here, and I find that's going to be negative 1,000 divided by negative 0.5 equals the first minus 1,000. And I find that A, right, is going to be 3,000 RPM clockwise, right? So we have like a 3-to-1 ratio here, or a 1-to-3 ratio, right? We're doing in this configuration here. If the arm is used as the input, we're going to make that sun, right? We made the sun, yeah, because the ring is fixed here. We're going to make the sun go 3 times as fast. That's pretty cool. In the second configuration, the sun gear is the input, okay, at 1,000 RPM. So that for us is the first, is how we're describing it. And F is equal to 1,000 RPM. And the arm is fixed, so NA is equal to 0. And then the ring is the output, so that's the NL is equal to who knows what. So putting this back into here, I say the last is NL minus, should be 0, divided by the first, should be an F, 1,000, and that should be 0 right there, right? And equal to negative 0.5. So we have the NL, not too hard to do, we get negative 500 RPM, or 500 RPM counterclockwise, right? So that's the thing that we experienced before, was when we fixed the arm, right? We had reversing taking place. C is part of this. The ring is the input at 1,000 RPM clockwise. Sun is fixed and the arm is the output, right? So the ring is the input, right? So the ring is the last, so that's at NL equals 1,000 RPM clockwise. The sun is fixed, so that's the first, NF is equal to 0, and then the arm is the output, so that's going to be the unknown. So once again, coming back up onto here, onto this equation right here, we have 1,000 minus NA divided by 0 minus NA is going to be equal to negative 0.5. And working that all out, I did a little algebra over to the side. I'll write it down here. All right, so I can put those over there, multiply by 0.5 NA, and I find that my NA is equal to 666.7 RPM, and it comes out positive, so we know that it's clockwise, right? So that's what happens when we have this configuration. That's the method by which we will try to establish what the relationship between the input and the output of a planetary gear. And for more complicated problems, we just use that same approach, but we adapt to what the scenario is going to be. And hopefully that is helpful. And that's a 12-minute video.